Hello everyone. For this lecture video, we will be discussing, as you can see here, we are done with this, and also with this one. Okay, so we are now discussing. We'll try to discuss this topic entitled machine epsilon. So for definition 21, it says here machine epsilon. This is the symbol. Is the smallest positive floating point number for which the this definition, the floating point of 1 plus epsilon is greater than 1. So meaning to say, you are going to find the smallest floating point, positive floating point number, such that this inequality will hold. Okay, so that's what we mean by machine epsilon. So anyway, it depends upon what operating system you are using. You are using 8-bit or 12-bit, 16-bit or 32 or 64-bit computer. So the epsilon is will vary. So what this definition means, it says that if we add 1 to any number less than epsilon, the machine computes the sum as 1.0. So with this one, the number, we know that the number 1.0 in its binary form is this one here. Okay, regardless of what we call this one, regardless of what kind of operating system or type. So if you are using an 8-bit, so count how many zeros are there. If you are using 32, 16 or 64 or 128, then this is the binary representation for the real number 1.0. So for 64-bit, the fractional part is up to a sub 53 is equal to 0 for 64-bit. Okay, so we want to find the smallest number that gives a sum larger than 1.0. So meaning to say, we are going to find the machine epsilon such that if you add to 1.0, that will give a sum larger than 1.0, the smallest number. So the number, this number, is epsilon, will depend whether we chop or round. Okay, so if we are going to use chopping, just like in the previous discussion in lecture chapter 1 part 3E. So actually this is part 3F. Okay, so if we are using chopping, this will be the form. So this is our 1.0 in binary form, and this is the smallest number, 0.0001, that we can add to the binary representation of 1, which is 1.00, that will give that will satisfy this one. Okay. So if we add these two numbers using binary addition, we know already how to add a binary number. I already discussed this one in I think in part 3, part 1 or part 2. Okay, so notice that 0.001, the one that we add, it is the smallest number, and if we try to convert this number to a decimal number, then the value is of course this one. We know this already because this first zero here is a sub 2, and since there are uh, if you remember your, what do you call this one, if you remember your our previous lecture, just like this one here, where are you, let's say this is the double precision or the 64-bit computer. We know that the exponent, the formula is this form, negative 1 to the s 1 times 1 point f, or f is the fractional part, and this f here is this one. There are 52 bit all in all. So as you can see, uh, we have the first fractional part, which is a sub 2 here, is if you remember, let's try to analyze it one. Okay, if you have let's say 0.0000 001, we know that this is a sub 50, a sub 2, a sub 3, and then a sub 53. Okay, we know that based on our previous discussion, I think this is the right one. This one here is I forgot the formula. A sub, let's say a sub n minus 1 up to a sub 1, a sub 0 point. This is the radix point. B sub 1, B sub 2, to B sub, and so on and so forth. Okay, we know that if this is base beta, you can write this one as the summation of a sub I starts from 1 to 0 to n times beta to the I. For this is the, we know that this is the integral part. Okay, for the fractional part, I don't know if you remember, for this one here we have b sub I starts from 1 to infinity times beta to the I. Okay, so as you can see here, this one here, sorry, just have another color, this one, the integral part is this one. Okay, at 1. So if we use the formula, this could be equal to 0 times 2 to the, since we are using base 2, this is base 2, 2 to the 1 for this first a sub 2, plus 0 times 2 to the 2 for the second one, up to this one here. Okay, so this will end up to since there are 52 bits all in all. Okay, there are 52. So if you remember, where are you, this one here, there are 52 bits, so this will end up to 1 times 2 to the 52. Okay, I think this is negative, right? This is negative at 1. Okay. mm, let's go back. Where are you? This one here. mm, am I right? Anyway, this is of course this is 0, and then we have is that negative? Let's recall. Where are you? Wait, just wait for a while. Yeah, that's negative. Okay, so this is negative 52. So what remains here is 2 to the negative 52. Okay, so as you can see here, we have how much is that? 2 to the negative, I'm sorry, I made a mistake. This is 2 to the negative 53. Okay, since 1/2 is 2 to the negative 1, so this is 52. Sorry, this is the right one. So let's open our or our text studio to change that mistake. We have in shopping, where are you? Sorry, this one. uh, this one here, we have 52. Okay, anyway, so that's how you are going to find the machine epsilon. Okay, so all you have to do is to determine the smallest number that we can add so that the sum will be different from 0. Okay, so that's the machine epsilon if we are using chopping. So how about if we are using rounding? Okay, so if you are going to round, remember there is when we round, notice that this number here that we are going to add will exceed uh, to 1 digit because we chop up to, I guess, 53 digits. Okay, so we rounded to 53 digits. Okay, so meaning to say, if we add this one, this is just the same, we can add 0 here. This, when we round, why is it that it will become like this? When we round to 53 digits, we add, okay, 1 to this one here, and after adding, sorry, after adding, if we will convert this one here, forget about this integral part, it will add up to uh, 53. Okay, it will add up to 53. Okay, since this one here has 53 no 50 54 digits. Okay, this one here, this one. Okay, this is the smallest. This is how you are going to convert to a decimal number, and the answer is 2 to the negative 53. The same method, just use this one. Okay, this idea. Okay, that's for rounding. Okay, so if we combine solution or those ideas, uh, if chopping you have 2 to the negative 52, if rounding we have 2 to the negative 53. So in remark 20, this remark 20, where are you, this one here, so this is our epsilon. Okay, so you can restate remark 20 as in this form, where epsilon is equal to this one. Okay, there is another definition for machine epsilon. It says here that it is the distance between 1.0 and the next floating point number, or next uh, positive. Okay, so floating point number. So for example, this is your original number and the next number will be this one. Okay, so the same idea or the same method that we used before, this next number, if you convert this one here, is the answer is 2 to the, I'm sorry, this is 2 to the negative 52. Sorry, again, I think I made a mistake. Where are you? The distance between, I think this one, 2 to the negative 52. Okay, so the same idea if you are going to use chopping or rounding. So in this alternative definition, machine epsilon is not based on I'm sorry, this definition is will not depend on chopping or rounding. Also note that the distance between two adjacent floating point numbers is not constant, but it is smaller for smaller values and larger for larger values. So that's it for machine epsilon. So maybe I'm going to ask you a question, if what do you call this one, if uh, the type of the operating system you are using is 32, so what is the machine epsilon for 8-bit computer, for 16-bit computer, or for 1 to 8-bit computer? So I'm going to ask that in the El Paso. For our next discussion is all about propagation of error. So in this section, we discuss the resulting error when chopping or rounding is used to approximate a real number by its machine version. Now imagine carrying out a long calculations. Just imagine many arithmetical operations, and at each step there is some error due to, say, rounding. So for example, that if you recall your algebra or in your trigonometry subject in high school, grade 11 or grade 12, if you remember all those calculations, funny moments, uh, the teacher told you, your teacher in math told you that when you try to solve a problem, do not as much as possible uh, use at least maybe 10, or in the calculator, copy all those numbers in the calculator, and after the final answer must be rounded, not the step that before arriving to that final answer. This is because if you are using, for example, in the first line of your work, if you are already using rounding or chopping, then your answer will be quite there's a big difference between the final answer and the original answer, with the exact answer, because before arriving at the final answer, you already done uh, rounding or chopping. Okay, so is when you try to uh, solve a algebra or trigonometry problem, do not round to two digits, digits as much as possible. uh, you should avoid in the first step. So uh, I think it will be best if you round the final answer, not the steps or the arithmetic operations in your calculation that you are going to round. Okay, well, anyway, this is what this statement is trying to say. So the question here is, would all the rounding errors accumulate and cause havoc? So yes, of course, since for example, if you are trying to solve a, let's say, the there is a tree somewhere here, the height of the tree, you are going to solve the height of the tree, this one. Okay, in trigonometry, so this is your theta. So if you do uh, rounding before getting the distance, you say this is y, this is x, this final distance here, if you do rounding to 1 or 2 decimal place here, then it's possible that you will get a big difference with the original answer. Okay, so that's what we mean by this statement. Okay, so what we will do here, so for a much simpler example, consider adding two real numbers. So let's have an example here. X and y. In the computer, the numbers are represented as this one, FL of x and FL of y. The sum, so if you get the sum, however, the computer can only represent its floating point version. So this is the floating point version, not the sum, not the sum here. So therefore the relative error is this one. Okay, that's the this is the relative error of summing, of getting the sum x plus y. Okay, so this section we will look at some specific examples where round off error can cause problems and how can we avoid those errors. So for example, let's have this section, subtraction of nearly equal quantities, almost equal, very close. Okay, so in this case we have cancellation of leading digits. For example, your x is 1.123456 and your y is 1.23447. So these are very close numbers, almost equal. Okay, so if you will get the difference x minus y, the resulting round of error using rounding and 6-digit arithmetic, this will be the result. Okay, so 6-digit, 1 2 3 4 5 6. So using rounding, this will become, you will add 1 to 5 since 6 is greater than 5. So we have here, we will add 1 2 3 4 5 6 5 also here since 7 is greater than 5. Okay, and we are using 6-digit arithmetic. So this is the floor, no, not floor, the floating point, the representation of x, real number x, and this is also for y. The absolute error due to rounding is this one. We already know how to solve this quantity here, and this is the absolute error, and this is the relative error. Okay, I did not put absolute value here because our x is positive. So this is for y. Okay, so from the relative errors, as you can see, we see that this is the relative error. We see that the floor, the FL of x and FL of y approximate x and y to 6 significant digits. Okay, you will see that here. Okay, so let's see how the error propagates when we subtract x minus y. So let's get the difference between x and y. So the actual difference is like this. 9 times 10 to the negative 6, 1, 2, 3, 4, 5, 6. So this is the actual difference without rounding, and the computer finds its difference. So how is the computer get the difference? First is the computer will compute floor of x, FL of x and FL of y, then taking their difference. So this is the taking the difference by its floating point representation, this one. So the result is 10 to the negative 5. The absolute error, the resulting absolute and relative errors are this form. This is easy to follow. Just substitute and study in your home using your notebook. And then this is the absolute error, this is the relative error. And then, where are you? This one here. Notice how large the relative error is compared to the absolute error. Okay, so if you look at the absolute error, this one here, and this is the absolute error and the relative error. So there's much big difference. So almost how many digits is the difference? It says here, the machine version of x minus y approximate x minus y to only 1 significant digits, as you can see here. Okay, using machine, this is for the computer. Why did this happen? When we subtract two numbers that are nearly equal, the leading digits of numbers cancel. So this is the leading digits, okay, cancel, and leaving a result close to rounding error. So in other words, the rounding error dominates the difference. So that's what happen if you are using what computer approximates or compute the difference between x and y. So it's different from a human point of view. Okay, so how about this topic? What if we divide by a small number? Okay, what if we divide by a small number? So for example, this is for the second part. For the first part, we have subtraction or subtraction of nearly equal quantities, and for this topic we have division by a small number. So for example, if you have your x, we have this form, and we compute x over 10 to the negative 5 in a computer with 5-digit arithmetic and rounding. So the floating point representation of x is this one, 5-digit. So 1, 2, 3, 4, 5, and d sub k plus 1 is greater than 5, so we add 1. Okay, we add 1 to 4, so this become 5. And if we compute the absolute error, we have 4 times 10 to the negative 6. So x minus this one is 4 times 10 to the negative 6, and the relative error, you can compute it at home, 9 times 10 to the negative 6. The computer computes. So what will be the result if we are using computer? See the floor of this one here, I think I made a mistake. This should be times. Sorry. Let's go back to where are you? Propagation of error. We have subtraction. This is division. And where's that error? Times 10 to the 5. This one here, FL of x, where are you? The exact, the computer computes, where are you? The computer computes this one. Sorry, but this is slash times. Okay, run. Okay, the computer computes the floor of this number to be equal to this one, 0.4445 times 10 to the 5, which has an absolute error of 0.4 compared to this one, and relative error which is 9 times, which is the same. Okay, and then the notice that the absolute error went from 4 times 10 to the negative 6, this one here, to 0.4. Okay, perhaps not surprisingly, because division by small number magnifies the absolute error but not the relative error. So as you can see here, the relative error is the same but the absolute error is not the same. Okay, so let's consider again this. This is very familiar in trigonometry. So consider the computation of 1 minus cosine x over sine x, where x is near 0. So closer to 0. For example, this problem, this is a problem where we have both subtraction of nearly equal quantities. We have this one here, 1 minus, and also a division, which happens in the numerator, and division by small number. So the topic that we discussed before and this one combines. So let's say, let's pick a number x which is 0.1, and let's continue with 5-digit rounding. So no, remember this equation, this expression. The FL of sine of 0.1 is this value, or cosine is this one, rounded to 5-digit. 1 2 3 4 5. 1 2 3 4 5. We have 6 here. Okay, sorry, this one is cannot be counted. 1 2 3 4 5. So remember your significant digits definition. And then the floor of this number is 0 point, not the floor, the floating point is this number. Okay, use your calculator. So the exact result to 8 digits is this one, 0.0500411708, and the relative error of this computation is 8.5 times 10 to the negative 4. Okay, so get the value of the original minus this one is the absolute error, then the relative error is divided this one. Next, we will see how to reduce this error using a simple algebraic identity. So to avoid, based on our discussion here, it says here in this section we will look at some specific examples where round off error can cause problems and how can we avoid them. See, we are in this phrase here. Okay, how can we avoid? So the it says here in our discussion is what if what if we apply simple algebraic identity like this one here. So what if what is this method, uh, rationalizing the numerator, okay, to arrive it in this form. I don't know if you remember your trigonometry, your algebra, I'm sorry. 1 minus cosine x over sine x. You can write it in this form. Okay, 1 plus cosine x, 1 plus cosine x. I don't know if you remember this. This is 1 plus 1 minus, sorry, 1 minus cosine squared x sine x, 1 plus cosine x. So the numerator becomes this becomes sine squared x over sine x, 1 plus cosine x. Okay, so use identity. This will become, we can cancel out this one here. We have sine x over 1 plus cosine x. Okay, so this is, sorry, hide. Okay, this one here. So using an identity, so one method to avoid an error is to use an identity. Okay, and then after that, as you can see here, removes both difficulties encountered before. There is no cancellation of significant digits, so or division by small number. So the result would be this one if we use x is equal to 0.1. So the relative error is 5.8 times 10 to the negative 6, and about a factor of 100 smaller than the error in the original computation. So what do we mean by 100 smaller? About a factor of 100 smaller than the error in the original computation. Remember the relative error, 5.8 times 10 to the negative 6. So as you can see here, where are you? This one, this is the relative error. So as you can see, about a factor of 100. The result in the original is 10 to the negative 4, and based on our discussion on ways on how to avoid accuracy, the result becomes more accurate and about a factor of 100. Okay, in the original we have 10 to the negative 4. In using this identity, we have 10 to the negative 6. Okay, so that's how you are going to avoid loss of accuracy. Okay, so we are now in this topic. So another example on how to avoid, let's have more example. If you remember your quadratic formula, this is the quadratic equation ax squared plus bx plus c, and we have the roots r sub 1 and r sub 2. So what if we approximate b to be equal to square root of b squared minus 4ac? So they are closer together. Then what will happen here is we will have a potential loss of precision including one of the roots due to cancellation. So let's have an example for this one here. This example, x squared minus 11x plus 1 is equal to 0. I know you are very familiar with this. So just use the quadratic formula our A is 1, our B is negative 11, our C is 1. So I think this is R2. I'm sorry. I think this is R2. Let's go back again. Where are you? Example 23. Example. Where's that example? R sub 2. Where are you? This one here. I think this one. R sub 2. Okay. So this must be R sub 2. We have 11 minus and 11 plus. So let's wait. Okay, so we have the correct notation. Rounded to 1, 2, 3, 4, 5, 6. So this is, I think this is what you will see in your calculator. Next, we will use 4-digit arithmetic with rounding to compute the roots. And as you can see here, the floor of no, not the floor, the floating point of the square root of 17 here, as you can see, this one, using 4-digit arithmetic is 10.82. Use your calculator, and if you plug in those values, you have R sub 1 is 10.91. For R sub, this is R sub 2. Sorry, I think we have to replace that one. R sub 2 is 0.09. Okay, so this is plus minus. Okay, so the relative error, as you can see here, relative error in R1, you have the original. This is R sub 1, which is this one here, this one, R sub 1 minus FL R sub 1 over R sub 1, this one here. The answer is 1.5 times 10 to the negative 4. For R2, we have 1.8 times 10 to the negative 2. Just do the same analogy. Notice the larger error, relative error in R sub 2 compared to that of R sub 1, and about a factor of 100, which is due to cancellation of leading digits, this one here, when you compute 11.0 minus 10.82. So how do we fix this problem? Okay, so first is we do rationalizing, just like what we did in this example 23. We do rationalizing. So I think one of the ways to avoid loss of accuracy is we have to rationalize to avoid subtraction. As you can see here, instead of subtraction, we use addition. Okay, so let's come back here. So rationalize R sub 2. After rationalizing, you will have this form. This is very easy. This is in your algebra. And if we compute, there's no problem with R1. So R sub R2 is really a problem here. In R1 we have plus, but in R2 we have minus. Okay, so what will happen if we use this one? Okay, so answer is 0.0916. So the new relative error will be this one. And if you compare the relative error before, which is times 10 to the negative 2, we improve, and we improve about a factor of 100. So 10 to the negative 2 for the new computation of relative error, we have 10 to the negative 4. So we improve a factor of 100. So even though in the way, a new way of computing R sub 2, there are two operations where rounding error happens instead of one. Okay. Okay, that's it for on how to avoid loss of accuracy. One way is you have to rationalize, and also maybe you can you will experience in this problem set number 4 what are the other ways on how to avoid loss of accuracy. So we have I guess this is problem set number 5, so maybe let's change this one. Problem set number 5, where are you? This one here, 5. Let's go to this one here. Where are your, this one here, we have problem set number, okay, we have a problem set in the part 3D, that's 4. I guess this is 5. Okay, so this is problem set number 5. Let's change this one to 5. 5. So problem set number 1. Okay, you can copy the x-intercept of the line passing through the points x sub 1, x sub 2, and x sub 2, x sub 1, y sub 1, x sub 2, y sub 2. So this is the formula, or you can use this form. Of course, y sub 1 is not equal to y sub 2. So what you will do here is, number 1, show that the formulas are equivalent to each other. 2, for number 1 letter B, skip, where are you? So this is problem set number 1. I don't know how to escape this. Okay, this one. For 1 letter B, compute the x-intercept using the formula and use 3-digit rounding arithmetic. And then finally, for 1 letter C, use Python to compute the x-intercept using the full precision of the device. You can use either one of the formulas, this one here. So using this result, compute the relative errors and absolute, then discuss which formula is better. That's for problem set number 5. Problem set 5, number 1, letter C. For problem set number 2, we have here, write two functions in Python to compute the binomial coefficient. This one here, using the following formulas. Then all you have to do is to experiment with various values for m and k to see which formula causes overflow first. So just make use of our previous discussion and get some values of m, particular number, m and k, and then use your functions for Python that you made, and then experiment for some values, and then discuss which formula is better, and uh, apply our previous discussion about ways on how to avoid loss of accuracy. For problem set number 3, this one here, where are you? Problem set number 3, this one. Polynomials can be evaluated in a nested form. We already discussed this idea. This is the polynomial, this one here, and the nested form is this one. Okay, and then after this, apply those definition using in this polynomial x squared plus 1.1 x minus 2.8. First is compute p of 3.5 using 3-digit rounding and 3-digit chopping arithmetic. Then compute the errors, absolute errors, or maybe you can include relative errors, and then write this formula in nested form for letter B. Compute 3.35 again, which is the same as here, using 3-digit rounding and chopping using this nested form, and then compute the absolute errors and then compare your result in A. Okay, so that's it for problem set number 3. Okay, so make use the idea of on how on our topic about propagation of error, ways on how to avoid loss of accuracy. So for the final topic, I think I have to put here sorry, I made a mistake. This is not a problem set. It says here sources of error in applied mathematics. Okay, mathematics. So this is not problem set, but these are the sources or list of potential sources of error when we solve a problem. The first one is error due to simplifying assumptions made in the development of mathematical model for the physical problem. So just like in our illustration before this one, if computing those values before arriving at the final answer, please do not round off to lower digits like 2, 3. As much as possible, you have to copy all those digits displayed in the calculator. So when you round your answer, it must be in the final answer. So do not round in the midway. Okay. Second is programming errors. So maybe if your program Python code is not correct, then you have an error. Number 3, uncertainty in physical data. About when you collect, there is an error in measuring or collecting the data. Number 4, we have machine errors like rounding, chopping, underflow, overflow, and so on and so forth. And also if you truncate No? Yes, if there's a truncation, so truncation error refers to error that results from the use of numerical methods in solving problem, such as evaluating a series by a finite sum, a definite integral by numerical multiplication method, or solving a differential equation by a numerical method. So this, I think we are finished with chapter 1. So next week probably we can start with chapter 2. Okay, so thank you so much for your time. God bless.